Wildberger. Up till now, we've developed a lot of linear algebra in a basic but somewhat abstract context. Now we want to move towards applying what we've learned to a wide variety of interesting applications. The first thing that we're going to talk about is how to apply linear algebra to the theory of polynomials. This is a very rich domain and a very important application of the subject. So let's start by telling you what a polynomial is. So here's an example of what I'm going to be calling a polynomial. This polynomial p is 3 minus 5 over 2 times alpha plus alpha cubed. And here's another one called q. It's 1 plus alpha minus alpha squared. In general, what a polynomial is for us, it's a formal expression consisting of a sum with rational coefficients of powers of alpha. Now there's a reason why I use alpha and not x or y or something else. And that's explained in my Math Foundations series, Math Foundations videos 57 and the ones following, where I relate the polynomial theory with more fundamental objects called polynumbers. But we're not going to need that, so I think it's enough for us just to accept that that's what a polynomial is. And we can do arithmetic with these polynomials in what I hope is a familiar way. So for example, we can take the polynomial p and we can multiply it by 4. The effect of that is simply to multiply all of the coefficients by 4. Or we can add the two polynomials, and we do that term by term. 3 plus 1 is 4, the minus 5 halves alpha plus alpha will be minus 3 halves, minus alpha squared plus alpha cubed. And there's a convention here that when a power of alpha has a 0 coefficient, we simply don't write it. But we're allowed, for example, to think of this as also being plus 0 times alpha to the 4. Or for example, up here, there was 0 component of alpha squared, and we didn't write that. Alright, so we have basic operations. We have scalar multiplication, just like this. We have addition. And with those two, we can form linear combinations. So for example, we can look at 4 times p plus 3 times q. 4 times this plus 3 times this, and you can check that that would be this polynomial. So this is an arithmetic that's just like vectors. And we're going to see that the parallel between vectors and polynomials is a very important one that we're going to exploit. Another important definition, the degree of the polynomial, that's the highest power of alpha that has a non-zero coefficient. So we look at all the powers of alpha that occur. There's the highest power. The power there is 3, so this polynomial has degree 3, while q would have degree 2. So a general polynomial looks like this. R equals a0, where a0 is some rational number, plus a1 alpha, plus a2 alpha squared, plus and so on all the way up to, say, a sub n alpha to the n. That's a general polynomial of degree n if a sub n is non-zero. And for us, as usual, the coefficients will always be rational numbers. I remind you, rational numbers are the basic framework for mathematics. Now, a polynomial like this is an abstract object. It's really just an expression. But it can be interpreted in a number of different ways. And one very important way of interpreting it is to think of the associated polynomial function, which is a function which you obtain by replacing all the occurrences of alpha with an x. And now we think of it as a function that inputs x and outputs this number. So for example, with p and q as before, the associated polynomial functions are p of x equals 3 minus 5 halves x plus x cubed, and q of x equals 1 plus x minus x squared. These are now functions that we can graph in the usual way in the xy coordinate, Cartesian coordinate framework. Now, so we're making a kind of a shift now to sort of calculus. This is now a two-dimensional representation of where we're going to graph functions. As such, it's normal to have the axes perpendicular. Up till now in this course, when we've been making coordinate axes, I've always stated that the axes don't necessarily have to be perpendicular. But when we're graphing functions in a calculus context, we're working with the Cartesian coordinate plane with perpendicular axes. However, the scaling on the two axes doesn't need to be the same. We can choose that conveniently so we can picture whatever we want in a decent way. So we can graph these two polynomials. This one here is a degree 2 polynomial. It's a parabola, which looks like this. This one here is a degree 3 polynomial, which we call a cubic. And it looks like this, roughly. And it goes through -2 here and through 3 here. And these numbers here are closely related to Golden ratios. Okay, when we graph a general polynomial function, the complexity of what we get is dependent on the degree. That's the main point. So degree 0, that would be when there's just a constant term. That's a constant function. It means that its graph looks like a straight horizontal line. So that's a degree 0 or constant polynomial function. If we have a degree 1 polynomial function, that's a line, a straight line like this. The only exception is this one here. This is not an example of a polynomial function. Degree 2 is always a parabola, either a parabola opening downwards like this, or a parabola opening upwards like this. And degree 3 is a cubic, which pretty well always looks like this. It starts down here, and then it goes up, and then it goes down a little bit, and goes up. Or it could do the negative. It could start here and go like that. And when we consider more general polynomials of higher degree, then the behavior is more complicated. So typically we expect a higher degree polynomial to be coming up smoothly, and then it goes down, and then it dips up, and comes down, and dips up, and comes down, and dips up again. And exactly where it dips up and how far and up and down it goes depends on the coefficients of that polynomial. Polynomials and polynomial functions are very important in mathematics. And some of the reasons are because, first of all, they're relatively simple objects. You only need a bunch of coefficients to specify a polynomial. They're easy to compute. We only require addition, subtraction, and multiplication of rational numbers to compute the value of a polynomial function. Division is not necessary. And another more subtle property is that in fact it turns out that they approximate arbitrary continuous functions on an interval. Let's make sure we understand what that means. Now suppose we have an interval on the horizontal axis. Let's say the interval from -1 to 1. And suppose that we have a continuous function f of x on that interval. So it means that we're starting at some definite point, we're ending at some definite point at the other end, and in between the function is doing something continuous. And here in green, this is an example of a continuous function. It's going up and down. It can have some abrupt changes in direction, but it's got to do so continuously. So there are peaks here, sharp points. Here it changes direction, becomes flat, but it's got to do so continuously everywhere. Now this kind of function I've shown you here is not a polynomial function, because polynomials never have this characteristic sort of V shape, or where you have two lines coming up, forming like a mountaintop. But any continuous function like this can be approximated to arbitrary precision by a polynomial function. And what does that mean? Well, it means that we can find a polynomial function in black here, which approximates it in the sense that if you ask for any degree of approximation, say 1/1000, then we can find a polynomial p of x so that the difference between the function's f's values and the polynomial p of x's values, the difference is always less than 1000 throughout the entire interval. We do that for a 1/100000th also. If we want to get within 1/100000th, then we'd have to choose a different polynomial, probably a bigger degree polynomial, and maybe the coefficients are very big, but nevertheless we could find one that approximates this function f of x within 1/100000th of whatever our scale is. That's an important theorem of calculus, and it shows why polynomial functions are so central, because they basically approximate everything else that's continuous. However, there is a price to be paid. For a very close approximation, you may have to go choose a rather high degree, and the polynomial may not be so easy to actually find. It's an important subject in numerical analysis, is to figure out how to find p of x given the function f of x. Another important application of polynomials is to interpolation. What does that mean? It means that we have a certain number of points in the plane, say a1, a2, a3, a4. We know exactly what those points are. And we want to draw a smooth function that goes through them. Perhaps to calculate intermediate values of this unknown function whose particular data points we know. So, the basic problem is to find a polynomial function, p of x, of the lowest degree possible, that pass through n given points. a1, coordinates x1, y1, down to an with coordinates xn, yn. And we expect that the polynomial p of x should be of degree n minus 1. So if you have 2 points, then 2 points can always be joined by a line, which is of degree 1. If you have 3 points, then you expect that a parabola or a quadratic polynomial function should go through those 3 points. If you have 4 points like these 4 here, you expect that a cubic can be found that goes through those 4 points. Alright, so that actually is the case, and then it's an interesting question, well, how does one actually find this polynomial that interpolates the given points? And that's where we first connect with linear algebra. That's basically a linear algebra problem. And the techniques that we've developed are perfectly suited to solve that problem. Let's have a look at it. So let's start out with the simplest example, where we just have 1 point. And then we want a polynomial function of the lowest possible degree whose graph passes through that point. So that's given by a constant function. The constant function is just the polynomial whose value is y1, the coefficient of y here. That's going to be a function, it's a constant function, that does pass through that point. More interesting is when we have 2 points, say x1, y1, x2, y2. This hopefully is a familiar problem to you that you've solved many times in high school. Let's have a look at it now from a slightly different point of view, from a linear algebra point of view, which is a little bit more general, allowing us to see a bigger picture. We're looking for a polynomial, p equals a0 plus a1 alpha. That's a general linear polynomial. The coefficients a0 and a1 here are unknowns. They're like numbers that we don't know. They're going to depend on these 2 points that we're given. We would like to find these 2 numbers. Alpha we're not interested in finding. That alpha is our formal parameter that just defines our polynomial. We're interested in solving for a0 and a1. And what do we require? Well, we require that this point be on the associated polynomial function, and we require that this point also be on that function. What does it mean? It means that when you substitute alpha replaced with x1, you're going to get y1. And when you replace alpha with x2, you're going to get y2. So we have 2 linear equations in a0 and a1. a0 plus a1 x1 equals y1, a0 plus a1 x2 equals y2. Those are 2 equations in a0 and a1, and the x1, y1, x2, and y2 are all constants that were assumed that we've been given. Okay, that's our basic kind of problem, how to solve a system with 2 variables. Let's do it. Alright, since we've been doing a lot of row reduction lately, let's use the row reduction approach to this problem. We set up the augmented matrix for this system. We row reduce this matrix. So I take row 2 minus row 1, getting that 0. And then here we have x2 minus x1 and y2 minus y1. It's a little bit more sophisticated than a lot of the examples because we've got variables now that we're working with. These are all numbers, but they're arbitrary numbers in the sense that we don't know exactly what they are. So we just have to work with the variable expression as we do the arithmetic. Okay, so what do we generally do then? It's already in row-reduced form. We'd like to get it in fully row-reduced form because we actually want a solution. So let's divide by this one here so that this entry is 1. Divide x by x2 minus x1, giving us this. But we have to kind of flag to ourselves, this only works if the x2 minus x1 is non-zero. If x2 equals x1, what would that mean geometrically? It would mean that our points have the same x-coordinate. It means that one is right on top of each other. And then the only line that goes through them would be a vertical line, which is not actually a polynomial equation. So it makes sense that something problematic happens if this denominator is 0. Okay, and then from this stage we would use this entry here to get rid of the x1. How would we do that? Well, we would take this row here and subtract x1 times this. So there, we've done that. That becomes 0. Now we have y1 minus x1 times this. Now when you're doing this, don't feel constrained by room. Make sure you have enough room on the right-hand side. The right-hand side does not need to be a little narrow column. Just expand it, write neatly and clearly so that everything fits in there. Now we have to simplify this thing here, get a common denominator, and then the numerator becomes y1 x2 minus y2 x1. And we can read off the solutions. Remember, our variables are a0 and a1. So there's a0 and there's a1. And then our line is this one here. Our polynomial is this one here. It's a0 plus a1 alpha. And y equals p of x is the equation of the line. Now I know you've all done this kind of problem with sort of high school maths before, with slopes and so on. So it might be interesting for you to work it out using high school algebra and make sure that you do in fact get the same answer. It's interesting to work out a problem like this with general variables instead of particular values sometimes. Even though it's more complicated, you can sort of see a pattern. One feels that one is understanding what's going on a little bit more with all these variables in here. Unless you're allergic, I suppose, to algebra. And I hope by now you're not allergic to it anymore. That you enjoy seeing an expression like this and a sort of a pleasant symmetry and attractiveness. But anyway, let's have a look at how it all works in a particular special case. Okay, so our example, let's find the line through minus 3, 2 and 4, 7. So there's our polynomial that we're going to try to fit to these 2 points. So we want these 2 points to satisfy the equation p of x equals y. Means when we replace alpha with minus 3, we should get 2. And when we replace alpha with 4, we should get 7. That's the system that we want to solve. Let's just do it in an alternate way to remind you of another way of doing it. Another way of doing it is to write the matrix equation like this, and then to multiply both sides by the inverse of this matrix. So a0, a1 is the inverse of this matrix times the vector 2, 7. Now what is the inverse of this matrix? Well, you have to calculate the determinant first. The determinant is 4 minus 3, that's 7. That's non-zero. It's non-zero, so it means the inverse does exist. And the inverse is 1 over the determinant times, for a 2 by 2, remember there's a sort of a special little formula that makes it pretty easy to find the inverse. We interchange the diagonal elements, 4 and 1, and we multiply the off-diagonal elements by minus 1. That only works in the 2 by 2 case. So there's the inverse. And then we do the matrix multiplication, and we get 1/7 of 29, 5. And so the coordinates of the polynomial are 29 over 7 and 5, 7. There's the polynomial, there's the polynomial function. And that's the line, the equation of the line, if you set it equal to y, that goes through those 2 points. And you can compare this with perhaps This looks like a familiar high school way that you might take delta y over delta x is the slope of the line obtained by change in y divided by the change in x. And you can check that it gives you the same equation. So the linear algebra approach is, well, first of all, it doesn't require a notion of slope, but it's much better because it generalizes to more than 2 points. If you understand what's happening, then when we have 3 points and we want to fit a polynomial through them, it's really the same story. Let's have a look at that. So we have 3 points now in the plane, x1, y1, x2, y2, x3, y3, and we would like to fit a parabola through those 3 points, a second degree polynomial. There's the polynomial that we're going to use. a0 plus a1 alpha plus a2 alpha squared. a0, a1, and a2 are unknown coefficients at this point that we're going to determine that depend on the 3 points. We want to figure out how to go from the 3 points to figuring out what a0, a1, and a2 have to be. So here's the associated polynomial function. Just replace the alphas with x's. And we require that this function pass through these 3 points. It means that if you plug in x1 for x, then the value should be y1. If you plug in x2 for x, you should get y2. And when you plug in x3 for x, you should get y3. So in practice, what will be known? In practice, all the x's and y's are known, and you have 3 equations in these 3 unknown numbers, a0, a1, and a2. So they are the variables in this system of equations. The coefficients are the variables, not the x's and the y's. Now, when you think of this as a system, like ax equals b, then it's the coefficient matrix over here that's going to be important. And that coefficient matrix has a very pleasant form. Just the coefficients of a0, a1, and a2. Along the first row, second row, third row. The rows look a lot the same, except the difference between x1, x2, and x3. This kind of matrix, where you start with 1 and then you have a variable and then the variable squared and then perhaps the variable cubed, increasing powers of some variable, then increasing powers of a second variable, increasing powers of a third variable, and so on. This is called a Vandermonde matrix. It's a very important matrix in linear algebra exactly because it comes from this problem. This is a very important problem. So, what do you have to do? Well, you have to solve this system of equations. And from a theoretical point of view, you have to understand this Vandermonde matrix, or another way of putting it is, ultimately you have to invert that Vandermonde matrix. And from that point of view, the determinant is particularly interesting. I'm going to ask you about the determinant in the exercises at the end. Alright, so the point is that to solve this kind of system, it's conceptually not much different from what we had in the 2x2 case, except we're working with a system of 3 equations in 3 unknowns, and we're expert in that. We know how to find the solution. In this case, the determinant is going to be non-zero precisely when the 3x values are distinct, meaning there'll always only be one solution. We won't have to worry, in fact, about any parameters. There'll be exactly one polynomial that goes through these 3 points of degree 2. And I hope now the pattern is pretty clear. If we had 4 points, I hope you can see what you would do. It would be exactly the same kind of thing. You would look for a polynomial of degree 3 with a0, a1, a2, and a3 as the unknown coefficients. Then you would write down 4 equations, one for each one of the points on the cubic. And then you would solve that system of 4 equations and 4 unknowns for the 4 variables that are the coefficients. After you've solved that, then you've found the polynomial, the cubic polynomial, that would go through the 4 points. And with 5, 6, 7 or more points, it's the same kind of story, although of course computationally a little bit challenging. There's lots of points. closely related to this set of ideas is an important topic in statistics called regression. And there what we have is a whole bunch of data points obtained from somewhere, which are points of the plane, in red here. And what we'd like to do is we'd like to fit a curve, say a line, through those points that somehow best approximate the data. This is different from the previous situation because we have lots of data points and we're fitting only a line to those data points. There's no way we're going to find a line that goes through all those points. We're looking for a line that best, in some sense, approximates the points. So we have enough to be able to explain what the general idea is here. The idea is a very important one. And I'm not going to give you the entire solution. That's really sort of a second year or second level course in linear algebra. But I think you can appreciate that what we've done so far sets up the theoretical framework for this problem. So what we think about is an unknown polynomial function of degree 1, a line. a0 plus a1x, we're trying to find that equation. What do we require? Well, we can't expect that all of these data points lie on the line, but we can expect that they're close. So if you plug x1 into the equation, you should get a number that's pretty close to y1. This means approximately, or close to y1. Similarly, when you plug in x2, you should get a value that's close to y2, all the way down to xn, close to yn. We can't solve the system exactly if there are equalities here, but we're looking for a good approximate solution. In matrix form, the equations that I wrote down can be written this way. This particular matrix, values 1x1, 1x2, up to 1xn, times this 2 vector, is approximately this n vector. So there are n equations here. There's our unknown vector that we're trying to find. And we know this vector has got n components. So the data, the points that were given, correspond to this column here and this column here. So what we're going to do is we're going to think of this as a linear transformation. It's a linear transformation setup. A times v is, well, not equal to, but close to y. So we're going to define the linear transformation determined by this matrix A. It goes from two-dimensional space to n-dimensional space. T of v is just multiplication by A. So we understand conceptually what that looks like. There's two-dimensional space. There's n-dimensional space. Axes y1, y2, all the way up to yn. Our linear transformation takes this plane into this n-dimensional space. And over here is the image. The image of the transformation, just those vectors over here, which are the image of something here. And that's going to be a plane over here, an honest-to-goodness two-dimensional plane. There's going to be no kernel in this case in general. And what's our problem? Well, over here we have the vector y, and the vector y here is definitely not in the image. Because this two-dimensional plane is a very small little part of this big n-dimensional space. It's almost impossible that this big vector is going to lie in this two-dimensional plane. But we're interested in the closest point in the plane to the vector. Okay, so we have to do a little bit of additional geometry here that we haven't done before, and that's why we're not going to actually look at the whole scenario. But the idea is pretty simple. We're going to look for the point in the plane which is the closest to the point y. In other words, if you drop a perpendicular to the plane, you're going to get some point y prime in the plane which is closest to y. And then what we're going to do is we're going to find the vector over here which is sent to y prime. That's going to be the solution that we want. That's the point whose image over here is closest to y. And so when we calculate the components, a0 and a1 of this point over here, we're getting the polynomial that we want, a0 plus a1 alpha. So that's the basic idea for regression, and it works like a charm, and it's basically our setup of linear algebra, understanding the image in terms of this geometry. You want to understand the geometry when you're doing regression, not just the algebra. So if you've understood that argument, you will also be able to see how to go up one level to the situation where we want to approximate a whole cloud of data points by a second degree polynomial or a parabola. So in this case, maybe our data is not along a line, but it's rather along some curve, and we want to find the best parabola or second degree curve that approximates the points. There's our polynomial function that we're considering. We have a whole bunch of data points, n data points. So we get n equations like this. Now each second degree on the left-hand side. Proceeding just as we did before, now we have a matrix with still n rows, but now 3 columns. Here, coefficients a0, a1, a2, and on the right-hand side our vector y1, y2 to yn. What we want to do is we're given the x's and the y's. We want to find the vector a0, a1, a2, which represents the polynomial, so that this combination is as close as possible to this vector over here. So we think about this also in terms of a linear transformation. We think of a transformation T going from 3-dimensional space, the space of vectors a0, a1, a2, to this n-dimensional space, given by multiplication by this particular coefficient matrix. And the idea is geometrically the same as it was before. We still think of the image over here as a subspace, in this case a 3-dimensional subspace, which still might be relatively small compared to all of the dimensions over here. Our given vector y is typically not in that subspace, but there will be a closest point in the subspace to that point y, obtained by going down perpendicularly. So that closest point, let's call it y prime, is in the image, and so we can find a vector over here that's sent to it. This vector here is what we're looking for. Its components will give us the polynomial which best fits the data. So we see the power of linear algebra, the power of geometric thinking, freed from constraints of just having to work in 2 or 3 dimensions. There are a lot of situations where we have more than 2 or 3 parameters, and geometrically that corresponds to working in a higher dimensional space. This is a very good example problem to keep in mind when you're thinking about that. The connection between polynomials and linear algebra is made clearer by realizing that polynomials form a linear space. Working with polynomials is not that different from working with vectors. And I want to talk about that now and establish some terminology that allows us to make sense of what that means. So let's fix a natural number n. And let's consider all the polynomials of degree less than or equal to n. These form what we might think of as a linear space. So informally, at this point, it means that we can add them and form scalar multiples. So let's be clear about that. So here is a space of polynomials of degree n or less. It consists of objects like this. Combinations of 1 alpha, alpha squared up to alpha to the n. Coefficients which are general rational numbers. And we don't insist that this last coefficient be non-zero. The coefficients can be anything that they want to be. So the polynomials of degree less than or equal to n. So this defines a type of mathematical object. We're not going to consider the set of all such things. So this symbol here does not represent a set. It just represents a type of object. We've identified this kind of object is going to be of interest to us. We're giving it a name. So what can we do with these polynomials of degree n or less? Well, here's 2 such, p and q, let's say, with coefficients a's, coefficients b's. Then we can add them, just the usual way we add polynomials. which would be to add the constant terms, to add the linear terms, and so on, all the way up to the nth power terms. So we're adding the coefficients component-wise. And another thing that we're allowed to do is we're allowed to multiply a polynomial by a scalar or a number. So lambda times p would just be the new polynomial whose coefficients are lambda a0, lambda a1, up to lambda an. So polynomials and vectors are pretty close, as you can see by the definitions here of what we mean by addition of polynomials and scalar multiplication. So our idea now is to relate this space of polynomials with the space of vectors that we've already been considering. And it turns out that Pn is pretty well the same as Vn plus 1. In other words, the space of polynomials of degree less than or equal to n is naturally identified or similar to or equivalent to the space of vectors with n plus 1 components. That's an idea. So we want to make that precise. We want to introduce some terminology that will allow us to say that this kind of object is really the same as this kind of object. And working with one is a lot like working with the other. This is a very powerful kind of way of transferring knowledge from one abstract situation to working with a lot of rather concrete situations that might look different, but essentially are the same mathematically. Let's have a look at a simple case to make it clear. So let's consider just polynomials of degree 2 or less. So we're just talking about objects that look like this. Now to connect these with vectors, column vectors, we're going to introduce a map or a function from polynomials of degree 2 or less to vectors with 3 components. And here is how we're going to define that map. It's very elementary and obvious. We're just going to take this polynomial and associate to it the vector of coefficients. Start with the polynomial, end up with the vector of coefficients. They're pretty much the same thing, aren't they? They look different, but this is a way of establishing a connection between these two mathematical objects. Now this map has a number of interesting properties that makes it what mathematicians call an isomorphism. Isomorphism is a fancy word for meaning it's a map that establishes kind of equality or equivalence between two seemingly different things. So what is the definition of an isomorphism in this case? Well, this map has 3 basic properties. The first of all, it's a bijection. Informally, what that means is that every polynomial is matched up with a vector, and every vector is matched up with a polynomial. That's informally what it means. Technically speaking, we have these terms surjective and injective. Surjective means that every vector over here is the image of some polynomial. In image kernel terms, it means that the image is all of V3. And injective means that no 2 polynomials go to the same vector. In our former terminology, that means that the kernel over here is just 0. Alternative notations for surjective are onto, that means the same, and injective or one-to-one, these are also equivalent terminologies. So right now, let's not get into the details of what these things mean. Let's just say that bijection means that this is a complete matching up between polynomials and vectors. Every polynomial gets a vector, every vector gets a polynomial, there are none left over, every boy gets a girl, everybody's happy. The other properties concern the additive structures and the scalar multiplication structures on both of these spaces. If we have 2 polynomials, we can add them, and then we can apply our transform phi. That's equal to 5p plus 5q. If we have a polynomial p and we multiply it by lambda, then phi of lambda p equals lambda phi of p. So you will, I hope, recognize these two properties of phi as just being our basic fundamental properties of a linear transformation. So that's what we're really saying here. So we have a linear transformation from this space to this space, which is also a bijection. It's a bijection, and that makes it an isomorphism. As far as we're concerned now in terms of linear spaces, these are pretty well the same thing. So everything that we know about this space, we can transfer to this space, and conversely, if we have a problem in this space, we can transfer it over here and work on it in maybe perhaps a more familiar setting. So if you've studied calculus, you probably like to think of polynomials in terms of their graphs, in terms of polynomials as functions. So what we're doing here is establishing a connection between certain kinds of functions and our abstract three-dimensional vector space. So over here are polynomials of degree 2 or less. Here's our phi isomorphism that we've talked about, sending this polynomial to the vector of coefficients. So we can now think about this transform as what it does to particular special polynomials. The simplest polynomial perhaps is the polynomial p equals 1 with just a single 1 there. That's sent to the vector 1, 0, 0, which was our standard basis vector in the first direction. Let's call it the A0 direction. Then another simple polynomial is the polynomial alpha, which corresponds to the function x. That would get mapped to 0, 1, 0, which is our second basis vector, usually in the y, or in this case the A1 direction. And the polynomial x squared, or alpha squared, right there represented, that would get mapped to 0, 0, 1, which would be our third basis vector, the one pointing in our third direction, say A2 direction. So these three different polynomial functions, degree 0, degree 1, degree 2, get transformed into our three basis vectors in our space. And if we take some more general polynomial in our space, say 1 plus alpha minus alpha squared, this parabola here, well, we can think of that as a linear combination of these three. And the transformation over here sends it to the vector 1, 1, minus 1 right there, which is just the corresponding combination of the three vectors over here. So it's a very nice setup, and next time we're going to see how this allows us to connect a lot of interesting aspects of calculus into a linear algebra setting. Exactly this kind of transformation, sending polynomials into vectors, allows us to think about calculus perhaps in a slightly new and interesting way. Alright, so time for some problems. First exercise, to find the line through these 2 points using linear algebra. Find the parabola, or second degree polynomial equation, through these 3 points. Find a cubic, or degree 3 polynomial, through these 4 points. And the second exercise, in the same kind of direction, but somewhat more abstractly, suppose we have 3 general points lying over x equals 1, x equals 2, x equals 3, but we don't know what the y coordinates are. So in terms of these 3 y coordinates, c1, c2, and c3, can you write down the parabola, second degree polynomial, that goes through the 3 points? The Vandermonde matrix determinant, interesting exercise to show that the determinant of this 3 by 3 matrix is the product of 3 factors: x1 minus x2, x2 minus x3, and x3 minus x1. So the determinant is 0 precisely when 2 or more of these 3 values are equal. It's called a Vandermonde determinant. And our last exercise is a little bit of an introduction to thinking about ideas of calculus from a linear algebra point of view. So I remind you that if you have a function, like a polynomial, you can take its derivative, represented here by this prime. And then if you take the derivative of this polynomial, you get a1 plus 2a2x. And I'm asking you to describe this derivative as a linear transformation from our space of polynomials of degree 2 or less to itself. So if you start with a polynomial of degree 2 or less, you end up with a polynomial of degree 2 or less. And you can check that this is a linear transformation. So the question is, what is the image? What is the kernel? Can you draw a picture of what this transformation does sort of geometrically in this three-dimensional space? Next time we're going to have a look at more polynomials, more connections between linear algebra and calculus. We're going to talk about bases of polynomial spaces. I hope you'll join me for that. I'm Wildberger. Thanks for listening.